Okay, now this goes into the classification of amino acids, and this is something that people will. I know whenever I took biochemistry, it was like you just had to hammer this into your head, like know the structures, know the structures, know the classification, everything like that. And it's almost like you begin to miss the forest for the trees and everything. So I don't want you to necessarily think about amino acids as polar or nonpolar, but I instead want you to think about what is that R group made up of. Okay, and so when we look at this R group, we've got glycine and alanine. Those are both small. Glycine is simply a hydrogen, alanine is a methyl group. Okay, then when we go on to proline, valine, leucine, isoleucine, methionine, what's happening with those? We've got another sort of, sorry, just a second. Okay, where'd my cursor go? Where'd my mouse go? It's there. I'm finding it. Okay, I'm sorry. Sorry about that. I'm back. So we've got glycine, alanine, proline, valine, leucine, isoleucine, methionine. Now, proline, valine, leucine, isoleucine, methionine, with the, sorry, remove methionine from that last description. We have nothing but carbons and hydrogens. These are hydrocarbons. Okay, what do you know about hydrocarbons? Well, they're going to generally not have any polarity in them. So they're going to be classified as nonpolar R groups. Now, I want you to temporarily look at these and just think about them as independent entities we don't really care about too much. We'll come back to them, but for a moment, let's just take a pause on them. The next group, we've got our aromatic group, or we have our aromatic R groups. We have our aromatic residues. Now, one of the things that's worth noting about these is that they kind of get bigger and bigger. Phenylalanine and tyrosine are fairly similar to one another. The difference is that tyrosine has that hydroxyl group. Tryptophan is a little bit wonky altogether, but remember that as your two-ring structured molecule. My next, or the next amino acids are going to be your polar uncharged residues. Excuse me, polar uncharged residues. And what you should recognize about them is that we've got a hydroxyl group. We've got another hydroxyl group on serine and threonine. We've got a cysteine on, or we've got a sulfhydryl group on cysteine. We've got this something that looks like a carboxylic acid, but we've thrown an NH2 on there in asparagine and glutamine. Okay, so these residues are all kind of distinct compared to those first ones, those nonpolar residues. So we've got different electronegative elements on these amino acids compared to those first amino acids. And if you think about those aromatic residues, well, those aromatic residues, that phenylalanine, that was a phenyl ring or a phenol ring, so that was nothing but hydrocarbons. If you compare that to the tyrosine, we're going to come back to all the residues in just a little bit, but that tyrosine, that has that hydroxide group, so that's possibly capable of hydrogen bonding, or, well, maybe it's a little bit more polar than that phenylalanine. And then that tryptophan has a whole bunch of stuff in it. So it's got nitrogen in the ring, and so that's going to make it a little bit more polar. But the place where I want you to start whenever it comes to learning my amino acid structure, I want you to start with these residues. These residues are your positively charged R groups. Lysine, arginine, and histidine. I recommend, and the reason that I went through those first few kind of quickly is because I recommend that you simplify it for yourself. You say, I'm going to learn 3 amino acid structures, and I am going to know those structures very well. Okay, lysine is also known by the 3-letter code LYS or the single letter code K. Arginine is known by the 3-letter code ARG or the 1-letter code R. Histidine is known by the 1-letter code H or the 3-letter code HIS. Okay, now these are classified as your positively charged residues because they are going to be overall positively charged at pH of 7. Okay. You'll also notice on here lysine and arginine have that positive charge kind of required. Now the histidine residue kind of stands out because this at a pH of 7, I know that I just gave you the definition that it's classified as positively charged. Um, this is actually not going to have a positive charge, but at a pH below 6.1, approximately 6.1, it has a positive charge. And I'm going to get back to those pHs in just a little bit whenever I show you the pKa's and everything like that. But what we're looking at here is 3 amino acids that can potentially have a positive charge on their R groups. None of the other amino acids that we've talked about have those positive charges. So when you think about amino acids, or what I want you to think about with amino acids is I want you to be thinking about what types of interactions could they be involved in. Well, if you have a positive charge, what does that tell you? That tells you that you're working with a cation. Okay, that cation, what's it probably going to do? It's probably going to attract an anion. So this lysine, this positively charged lysine, that would be a lovely friend for meeting up with a chloride ion or something like that. Or a negatively charged amino acid, aspartate and glutamate. I like these two residues because they are very similar to one another. If you know the structure of glutamate, then you know the structure of aspartate. These two residues at a physiological pH, their R groups are going to be negatively charged. Now, I'm not going to get too into it right now, but we can talk about overall charges. What we want to do is we want to sum up the charges. Negative, that's a -1. That's a +1, -1. Okay, so plus, minus, minus equals, well, these two cancel one another out, minus. Plus, minus, minus equals, again, these two cancel one another out. The overall charge for this molecule is minus. Now, it's valuable to appreciate that, but when you start talking about charges as they contribute to a peptide or of an overall protein, then you're going to talk about it a little bit differently because you might not be concerned with the N and C termini. But these are all of the amino acids, all of the proteinogenic amino acids. Now, to look at them a different way, here they all are. I asked you to start with, or I recommended that you start with your positively charged residues. So I would say learn these first, then move on to your negatively charged residues. Learn those second, then just kind of for the sake of incrementally growing, I would go on to my aromatic residues, then I would go on to my polar residues, and finally my non-polar residues. I know that I started this discussion by saying I don't really want you to worry about organizing them so much. It is helpful, but what I want you to do is I want you to think about them in terms of what types of interactions could they be involved in. Okay, so if you think about one of the things that we talked about with water, we talked about the hydrophobic effect. Two things that didn't necessarily want to associate with water basically being forced together. Well, let's look at all of these residues. Which residues do you think would be able to, and I'm just going to use a check mark by them, which residues do you think would be capable of forming a bond with water? Well, we've got that permanent dipole with water, so glutamate and aspartate, yep, they would be able to. Histidine, arginine and lysine, those are all potentially positively charged, so yeah, I'm going to give those a check mark. If I go to my aromatic residues, well, that phenylalanine, probably not, so I'm going to put a frowny face. That tyrosine, well, it's got that hydroxide group right there, so that's a good candidate for hydrogen bonding, so I would put a check there. If we talk about tryptophan, well, remember when we're forming hydrogen bonds, we want a nitrogen to a hydrogen and basically be able to have that hydrogen bond donor. Well, tryptophan's a pretty good candidate because it has that nitrogen. So I'm going to say, yeah, that could form a hydrogen bond with water. Serine, threonine, cysteine, asparagine, glutamine, all of these are good candidates because they all bring something that gives them a little bit of polarity, and all give them an electronegative element bound to a nitrogen, making it possible for them to hydrogen bond. Um, Compared to your nonpolar residues, glycine, alanine, valine, leucine, isoleucine, methionine. Well, you've got that methionine that's got a sulfur. That's neat. Is that electronegative element, or is that electronegative enough for hydrogen bonding? It really isn't. So methionine is not really a good candidate for any sort of hydrogen bonding, or yeah, hydrogen bonding with water. So all of these guys, frowny faces. All of these guys, what are they going to want to do? Well, they're not going to want to be around water, and so they're going to be kind of forced together. They're nonpolar, they're hydrophobic residues. Those will all interact with one another. Because when you learn amino acid structures, you need to be focusing on what types of interactions exist between those different residues. Okay, so if we take histidine, is histidine going to want to form a bond with histidine at an appropriate pH where it's positively charged? Or actually, heck, forget that. Histidine, by having that NH, that's a good candidate for hydrogen bonding. Do you think it's going to want to form a bond with leucine? No, not at all. It's going to want to form a bond with something that can donate a hydrogen ion, or donate hydrogen for a hydrogen bond. Then if you talk about something like proline, for instance, proline's got a really kind of wonky and crazy R group. You think that's going to want to form a bond with histidine? No, it's probably not, because it's not going to be good at forming hydrogen bonds. All right, well, this was lengthy, and I'm saying this now. I'm probably going to break this into 2 different videos. If you're watching the end of an 18-minute video, though, that means I didn't break it into 2 different videos. If you're watching the end of like a 9-minute long video, then pat on the back for me. All right, well, have a good one. Amino acids, they're tough, but stick with them. All right, have a good one.